Diffusion is the mass transfer of substance through another due to a concentration gradient. The tendency of particles to move randomly leads to a more and more uniform concentration in the space that the substance fills, according to the diagram behind me. Diffusion coefficients are assigned to specific pairs of species, for example, carbon dioxide and air, to describe how quickly they diffuse into each other. There are two main types of diffusion, equimolar counterdiffusion and A through stagnant B. Equimolar counterdiffusion occurs when both substances diffuse through each other at the same rate. A through stagnant B occurs when one substance diffuses through another stationary substance. An example of A through stagnant B is evaporation. The main equation used to calculate diffusion is Fick's law, where the molar flux J in moles per centimeter squared per second equals the diffusion coefficient, or diffusivity D, in centimeters squared per second, times the concentration gradient dC in moles per centimeter cubed over dx, the length and the direction of movement, in centimeters. Many diffusion coefficients at specific temperatures for specific pairs of species have been found experimentally and reported. Coefficients not listed can be found using known values in the following relationship between diffusivity D and molecular weight M.
One way diffusion is relevant to hazardous waste is in hazardous landfill design. A clay liner or a geomembrane must be used to line the ground before filling the landfill because these have a very low permeability, so very little diffusion will occur through the liner. You can use the diffusivity coefficient to determine the rate of diffusion through the liner. Knowing this, you can choose a thickness that will prevent leakage of the hazardous materials for any desired length of time. Another way the diffusion coefficient is used is in groundwater contamination. It is needed when finding how far a contaminant has spread. The movement of a pollutant in groundwater, called hydrodynamic dispersion, includes molecular diffusion, in which case you'll need the diffusivity constant, also the velocity of the water, and the turbulence and mixing.
Okay, we're going to go over a couple ways to estimate D, which is the diffusion coefficient. First sample problem we're going to do is just estimating it based on tabulated values. So the question, estimate the diffusion coefficient of ethyl alcohol in water. We're going to do this by using the tabulated values from similar compounds, and we're going to show that it gives you about the same D value that you would have gotten from the table straight up. So we're looking for ethyl alcohol here. We have our table, or our partial table. We have methyl alcohol, butyl alcohol, and ethyl alcohol. These are our diffusion coefficients, molecular weights, and temperature in degrees Celsius. So what we're going to do is we're going to estimate it from methyl alcohol and butyl alcohol and then average it for a estimated D value. So for methyl alcohol, we're going to use this equation right here. Final D equals D2, ratio of the molecular weights to the 1/2 power. So we come up here, get our D. This is the ratio of the molecular weights. We got the methyl alcohol molecular weight over the ethyl alcohol molecular weight, and that's going to give us 1.46 times 10 to the negative fifth. Similarly, we're going to do the same thing for butyl alcohol and ethyl alcohol. Right here, we're going to get 0.71 times 10 to the negative fifth for our D. The units on both of those are going to be centimeters squared to 2 centimeters squared over seconds. And our mean average of these is going to give us 1.09 times 10 to the negative fifth centimeters squared per second. So that is pretty close to the value that the table would have given us straight up. It's 1.24 times 10 to the negative fifth, and I believe that gives us about a 12% difference, which is fairly close given the accuracy of the science. Okay, our second method for estimating the diffusion coefficient is called the Wilkie-Chang method. So here's our example, number 2. We're going to estimate the diffusion coefficient of methylphenyl sulfide in water at 20 degrees Celsius. So here's our methylphenyl sulfide, the molecular weight of 124 grams per moles. The Wilkie-Chang equation is shown right here. It's our diffusion coefficient equals 5 times 10 to the negative second times temperature divided by the product of the viscosity of water times our mole volume to the 0.6. So a couple of these things are already given. We have our molecular weight, viscosity of water we're going to use is 0.89, and we're going to get our molar volume from the table based on the components of methylphenyl sulfide, which is going to give us 158.8 centimeters cubed per mole. Alright, so we don't have to do much, we just kind of have to plug and chug on this one. We're going to have our diffusion coefficient equals 5 times 10 to the negative 7th. Our temperature going with 25 degrees Celsius, which is going to be in Kelvin. So it's 298 degrees Kelvin, or 298 Kelvin. Viscosity of water, 0.89. And finally our volume, 158.8 to the 0.6. And that will give us about 7.87 times 10 to the negative 6 centimeters squared per second. That will be our diffusion coefficient.